welcome to DigiPath Digest. We are in our normal series because we just finished the 7-part AI series. We went through all the papers from modern pathology about AI in pathology. They had a super cool series that we are now into a more concise version to enrich the pathology AI makeover course. And we are going to update the book with the information from all those live streams and all those papers. So we start with enhancing malignancy detection and tumor classification in pathology reports, comparative evaluation of large language models. This is so cool because the large language models are so part of our life now. I'm so happy that this AI tool made it into the mainstream. This is a group from Austria. And what they did, the background of this paper is that cancer registries, they need accurate and efficient documentation. And manual methods are obviously time-consuming and error-prone. So time-consuming and error-prone, everything that we do manually, obviously. So the objective of the study was to evaluate the effectiveness of LLMs in classifying malignancies and detecting tumor types from pathology reports. So we're working with text, we're not working with images here. And the cool thing that they described in the second paper as well, that we're going to talk about in a minute, was that they were using a synthetic data set of 227 reports. They made them up. They made synthetic reports, which is super cool. Synthetic data is I would say it's a new discipline in the medical field where you can actually test tools on synthetic data. Fantastic. And then they checked the performance of 4 LLMs and score-based algorithm, and it was compared against expert-labeled gold standards. And the LLMs, specifically GPT-4o and LLaMA 3.3, demonstrated high sensitivity and specificity in both malignancy detection and tumor classification, outperforming traditional algorithms. So they had this score-based algorithm, and the language models outperformed them. And the conclusion is that language models enhance the accuracy and efficiency of cancer data classification. And I like this thing, text mining. Data mining was something that was the hype. It's a discipline, but the first time I heard about it was maybe 5-7 years ago. Data mining. And now we can do text mining. Imagine how cool it is. You can just give this language model all the reports that you have, and you don't have to the control whatever that is that you search. Control F, I think. I don't know. Control F is for searching. You don't have to do that manually. I'm thinking how many reports I had to go through, years of reports for my PhD to find the diagnosis that then I had to go into the archive to dig for slides and reevaluate those slides. How much easier my life would have been with large language models and also with whole slide images of all these slides that I had to dig out of the archive. But you know what? That's okay. The people who now have large language models are going to have different stories to tell in 10 years when the new thing comes and they are like, oh, we only had LLMs and now we have this new thing, and it is so much more efficient. So going back to our artificial data. So the same group from Austria, they developed these synthetic oncology pathology data sets for large language model evaluation in medical text classification. So they have a data set of these reports where you can test against. So the background here is, let's say where we published this, where this was published in Stud Health Techno Informatics. Large language models offer promising application in oncology pathology report classification, and probably in any medical report classification, improving efficiency, accuracy, and providing automation. And the use of real patient data is restricted due to legal and ethical concerns, right? It's always a concern when we use patient data because we want it to be de-identified, but there have been several publications saying, oh, no matter how you de-identify it, you can still identify it. So, mixed feelings about it and different opinions on this. So one of the solutions that can be used is that to develop a synthetic data set, right? So this study aimed to develop synthetic oncology pathology data set to serve as benchmark for LLM evaluation, enabling reproducibility and privacy preserving AI research. So they created these 227 synthetic reports. They were generated using Microsoft Copilot, ChatGPT Plus, and Perplexity Pro. What is ChatGPT Plus? Is that the 4.0 that you have to pay for? Anyway, I think I loved it because they did it to ensure a structural and linguistic diversity, right? So they use different models to make this data set as versatile, diverse as possible with different models. How cool. Like, it's just so surreal that we can now generate this artificially. So this is amazing. And the data set included cases of prostate, 75, lung, breast cancer, and evenly distributed between malignant and benign. Like, you can synthesize the distribution of whatever you're looking for, like a challenge in those pathology and medical space in general is that the prevalence of disease is always lower, right? So you have this, I don't remember, there's a name and for this phenomenon, like data that is underrepresented, but now you can totally just generate the data you want. I don't think we're quite there with images, but with text, you totally can. And then an expert reads through it, takes out the nonsense, like I did for my speech. Like, I was semi-generating it with AI, but then like I went through it super thoroughly, took out everything that sounded like ChatGPT and put some other stuff in. Anyway, long story short, you can do that with a report as well. So it's like the other way around. Like, when you generate ground truth pathology scoring, pathology report writing, whatever, diagnosis, right? Annotations, specifically annotations, you have this subjectivity of a human that you check against. And here it's the other way around. You generate something automatically, and then the human checks if this is correct. So kind of a flip of roles. So the reports were reviewed and classified by 3 independent cancer registrars. And the results say that the data set provides a structured, clinically relevant benchmark for evaluating LM performance in pathology text classification. And it enables AI. Yeah, so we now have a data set that we can check models against, which is super cool. This I'm going to just mention by title and not go into it, but there is an interoperability framework of the European health data space for secondary use of data, and interactive European interoperability framework-based standards compliance toolkit for AI-driven projects. Why am I mentioning this? Because it's a new guideline that we can use. Somebody already developed it. And I got inspired to highlight these guidelines from the 7-part series. There was one specific article about regulatory frameworks and things like that. And there's always this repeated sentence. I don't want to say slogan, but a repeated sentence. Oh, the regulators are lagging behind. The regulators don't know. There was a huge table with different regulations. So I think we're underestimating our regulators. They produce a lot of guidances and they put a lot of thought into those guidances. So we don't have to reinvent the wheel. We can go check the guidances. And now we have an interoperability framework in Europe. So we can check that. And that was published in Journal of Medical Internet Research. I don't know. I'll do my due diligence next time on all the journals that we're discussing. So there is a framework. Oh, this one. I have to talk about this one because these people are from Poland. Hi to all the authors of the publication called Efficient Annotation Bootstrapping for Cell Identification in Follicular Lymphoma. And these people are in Poznań, where I used to go to high school. My friends, this is where I went to high school. Anything else? Oh, yeah. These are like familiar places. This Maria Skłodowska-Curie National Research Institute for Oncology Tumor Pathology Department. I was a patient of that one with my thyroid cancer when I had thyroid cancer. So I was a regular visitor. And there you can see my scar. So when they took my cancer out, they took it somewhere else in Szczecin. But then I would go for, first I went for radioactive iodine therapy there. But yeah, I would like travel to this center a couple of times, like for 5 years or something like that. So that was that. Let me make myself small again. So let's check what they did, these groups, and something else. We also have the capital, Warsaw. So what they have everything? Yeah. There's another heart here. Haha. Okay. So background and objective. Obviously, annotations are a bottleneck. So we know anybody who ever annotated anything for deep learning or any other image analysis model development knows that acquiring a substantial number of annotations for developing deep learning algorithms remains a bottleneck. And the annotation process is inherently biased due to various constraints, labor shortages, high costs, time inefficiencies, and strongly imbalanced distribution of labels. Here, the class imbalance was the thing I was looking for in this other paper. Class imbalance. So strongly imbalanced distribution of labels means that there's more healthy than sick always, hopefully, in the population. And that translates into the consequences for model training, right? If we have an underrepresented class, then we don't have so much training data to train on. So then if we have synthetic data, we can generate as much of this underrepresented class, as many examples as we want. In this case, we are talking about images. In the previous case, we were talking about text. So text is easier now, but image is catching up, guys. Like, probably next year we're going to be talking about, if they don't do it, like I would imagine, for like cell classification, not like whole tissue architecture, but I think it's going to come soon. So, and they compare 3 distinct approaches to annotation: bootstrapping, extensive manual annotations. Who did that? Raise your hand. Yes, I did a lot of that. Active learning and weak supervision. So active learning is going to be, you start annotating and then the model, like in a system that learns as you annotate. And then it shows you examples of something that it thinks is the class you are annotating right now. And then you can click yes or no, yes, no. So it speeds up the process as well. And then weak supervision, where you don't do like detailed annotations, but you give a weak label. And they propose a hybrid architecture for centroblast and centrocyte detection from whole slide images based on a custom cell encoder and contextual encoding derived from foundation models for digital pathology. So this is cool because they are using foundation models. We have not heard about foundation models for like 3 abstracts. Well, actually, the large language models are foundation models. So we didn't hear the word foundation models for 3 abstracts, guys. Anyway, they use foundation, the contextual encoding, and they collected data sets from 41 whole slide images. I was a little under impressed with 41 whole slide images, but you know what? If that's enough data, then that's enough data. And they had it scanned with 20x objective lens, and the resolution was 0.25 micrometer per pixel. That's a lot of cells, like 12,000 cells. Annotations were gathered. So I guess they were, because we're lymphoma and they're doing cell annotations. So I guess 41 slides was enough. And we don't need to do more than that. And results: proposed active learning workflow led to almost 2-fold increase in the number of samples within the minority class. And the best bootstrapping method improved the overall performance of the detection algorithm by 18 percentage points, yielding macro average F1 score precision and recall of 63%. I would like to see it higher, but maybe this macro average F1 score is like very average, and actually for some classes it's better. We would need to go into the paper to figure that out. But yeah, different ways of streamlining annotations, and they're working, they're improving. And now let's discover why there's a heart here. The heart here is because the underlying people are actually my colleagues from my day job from Charles River Laboratories. So, of course, I had to review this one. It's TalksPath, and it's our last paper. So, I know that many of my digital pathology trailblazers are more in the clinical space, but if you are in doing image analysis in any shape or form, this is going to be interesting for you as well. So, what's happening here is that thyroid tissue is sensitive to the effects of endocrine disrupting substances. Yes, right. And histopathological analysis of rat thyroid gland is the gold standard for the evaluation of agrochemical effects on the thyroid. So you may know that for drug development, for any work, everything that you will get ever as a prescription drug had some tox safety evaluation, toxicologic safety, but not only that, also agrochemical substances. And so that's how they tested. They checked the rat thyroid gland in a histopathological evaluation. There is a high degree of variability in the appearance of the rat thyroid gland. And what does that mean? That toxicologic pathologists often struggle to decide and be consistent to apply a threshold for recording a low-grade thyroid follicular hypertrophy. So when it's low grade, it's going to be very subtle. So then always around the threshold in whichever visual estimation of amount, size, or anything, around the threshold, there's always going to be disagreement, regardless whether it's this use case or IHC quantification or anything like that. So one time I went to this PDL1 scoring workshop with a German MD pathologist, and for different companion diagnostics, you had a different threshold for actually prescribing the drug. And for something it was like 50%, something was 10%. Basically below that, you don't give the drug, and above this certain threshold, you give the drug. So they were trying to visually train us to be more consistent. But no matter how much they tried, it was like half-day workshop or something, always around the threshold, when they made us raise hands, half of the people would say below the threshold, half of the people would say above the threshold. So that means do image analysis. Don't ask people around the threshold. There's always going to be 50-50 chance that you are wrong. And you don't want to do this to patients. So that's why I'm an advocate for image analysis. And that's what they did here. This was a project where they developed a deep learning image analysis solution that provides a quantitative score based on the morphological measurements of individual follicles. And this can be integrated into standard pathology workflow. They did it with UNet convolution deep learning neural network, and it identifies the various tissue components of the thyroid gland, and it delineates individual follicles. And then they created so they did this on the image analysis side, and then they figured out dependent variables, or how are they gonna calculate the thyroid, these thyroid activity score, so how active the thyroid based on this. And that was superior to the mean epithelial area approach when compared with pathologist scores. And here we have this chicken and egg situation. They were comparing it to pathologist scores, and they say at the beginning, well, the pathologists are inconsistent. But that's not specific to this particular paper. This is always the gold standard paradox. It's my favorite paper that I cite from a friend of mine, Dr. Famke Effner. So yeah, that's it for today. Thank you so much. And I talk to you in the next episode.